Okay, Assalamualaikum and good morning.
Good morning, sir.
Okay, thank you. Okay, so today's session we still in the chapter one. Okay, before I forgot, okay, I already set the date for your midterm exam. Okay, we will detail out after this. Forgot about the date, but it's on week 6. Now we are on week second week. So now your midterm we had on week 6 on Thursday night, 8 to 10. Okay. So this one just a yearly reminder lah. Okay, after this I will detail out and we blast on the WhatsApp group and Kalam system lah. Okay. And please write your name and your matrix number on chatbot for my attendance record lah. Okay. So we continue our lecture. Okay, so we start this slide from yesterday class. Okay, so now we go for the next subchapter lah, which is classification of vibrations. Okay, so there is a few kind of motion lah in vibrations. Okay, first the simple harmonics motion. So harmonics motion, which is the motion can be represented into sine wave. Okay. So this one, there I have detailed out from the yesterday class. So which is by mathematically we can represent as x equal to a sine omega t plus theta or sine. Okay. So this one is the most common vibration response lah, especially for the single degree of freedom system. Okay, so if you give the initial disturbance, then the system will oscillate with this kind of motion. Okay, so A maximum amplitude, omega is the frequency of oscillation, how fast is oscillate lah. Okay, and psi is a phase angle where it start lah. If the motion we record start from equilibrium position, then we can declare as a theta equal to 0. Okay, so this one in detail lah. So x instantaneous displacement. Okay, because we know that when there is a motion, the value for displacement is not constant lah. So it's depend to times lah. So when the time change, the position also change. Okay. And as mentioned before, so A is maximum amplitude, omega is angular velocity, which is the unit is radian over second, theta is phase angle in radians. Actually, phase angle doesn't matter, you can represent in radian or degree. Okay, so but you must put a symbol for degree. So F is frequency, so which is the relationship with the omega, which is equal to 2 pi f. Okay, so T is a cycle period, which is the times taken to complete one oscillation, which is T equal to 1 over F lah, if you mentioned. Or F equal to 1 over T. So F can be represent many type of frequency lah. It can be natural frequency if it's oscillate by free vibrations. And characteristic frequency same lah, same with natural frequency, fundamental frequency, resonant, normal frequency. So just the same frequency, which is using different term lah. Okay, but it also can be the excitation frequency, for example. So if you have a motor, then the motor speed can be the speed of the frequency lah. So it's depend on the type of force vibration. Okay, this one is a motion This one have animation. Okay. So just look at this the red dot lah. So the motion goes up and down. Okay. So this is how we measure lah. So actually it's about the angle lah. So the angle is equal to omega t. Okay. So one complete oscillation is equivalent to 2 pi radians lah, or 360 degree. So this is how we can represent simple harmonics. So by naked eye, we can just look at the motion just goes up and down, but it's actually something like this. So which is can be represented into sinusoidal wave. Okay, then when talk about the motions, for the vibrations parameter, there is three type of parameters to measure the vibrations. Can measure in displacement, velocity, and accelerations. Okay, so for the measurements, normally we measure the displacement and accelerations. Velocity normally just come out from the integration or differentiation. Okay, so displacement normally use the proximity probe, the eddy current probe, something like that FVDT. Okay, and then accelerations is commonly used in industrial application, which is you can acquire using the accelerometer. Okay, but in the actual measurements, the value of velocity actually one of the most important because velocity is one of the most stable value as compared to the displacement and accelerations. So that's why in most of the standard, the ISO standard, the Energy Institute standard normally use the vibration in the units of velocity okay. So because displacement, if you do the measurement for displacement for the low frequency, which is meaning that the kind of motion is very slow, then the best sensor you use is measured by displacement however, when you go for the high frequency, then the error is increased it's vice versa to the accelerations. Okay, so accelerations is can perform very well for the high frequency. So which is if the vibration is very high, which is high frequency So the times taken to complete one peak oscillation is very small. So meaning that that one is high vibration, high frequency vibrations. It's different. High vibration meaning that the intensity is increased, so meaning that the high amplitude. So this one is high vibration. But when talk about high frequency, meaning that it's vibrate in it's faster vibration. So in terms of time. Okay. So for the acceleration, if you're using the accelerometer can measure very good high frequency range. But when we go for the low frequency, there is error in the value measured value okay. So the displacement, this one just if we represent as a sinusoidal wave, this one for the field vibration so which is a simple harmonic motion. If we can represent the displacement as a sine omega t, okay, and then the velocity is a we can get by differentiate the displacement okay. So displacement velocity is as we use as prime or as dot like that okay. So we integrate sine got cos, okay, and then omega measure differentiate sine omega t, got omega put in front of a sine, okay. So the maximum amplitude is omega a, okay, and then cos omega t okay. So cos omega t, can see that the color maybe this one is magenta okay. So it start from here so this one is cos function, okay. So equivalent to sine omega t plus pi over 2 which is 90 degree out of phase, okay. So start from here, okay. So the amplitude is depend on omega a so if low frequency which is the amplitude can be lower than displacement lah. And then if high frequency, the amplitude can be higher. Okay, and then acceleration. So acceleration, we can double differentiation of the displacement. We can just differentiate the velocity lah. Okay, so which is equivalent to minus because cos, when we differentiate we got minus sign lah, so that's why it's minus here. Omega square a sine omega t lah. Okay, as we can represent a sine omega t is equivalent to x, so which is equivalent to minus omega square x. Okay, so the amplitude is depend on the speed itself. Higher speed, higher intensity for the acceleration units. And the x value, the difference is a negative unit. So negative is meaning that it's a 180 degree out of phase or pi radians out of phase. So that's why it always move in the opposite direction of displacement. So if a displacement move in upward direction, the acceleration will goes the opposite direction lah. Okay, so which is goes to downward. Negative unit lah. So that's the relationship between displacement, velocity, and acceleration. This one is very important lah. It mostly used to derive the Morse equation in the subject. Okay, so this one I think I have already showed to you. This Takuma bridge, how it's failed. Okay, just keep it. The first lecture I already show you. Okay, so actually this due to the vortex shading lah. So that's why we want to study what is the I mean the resonant effect lah. Why we study the dynamics. Okay, so you see that this is what we call as a vortex shading lah. So vortex shading, which is the wind. So when the flow towards the bridge, okay, so it can create the vortex. Okay, so vortex for this case, it can create the harmonics excitation lah. Okay, so this is due to the structure weakness because this vortex shading is coincide with the one of its natural frequency lah. So that's why even
yeah. Slide tidak gerak, masih di slide number 12.
Oh, tak bergerak
ya.
Sorry.
Okay.
Oh, yang ni tak keluar tadi
Tak, sir. Just stuck dekat slide number 12 tadi.
Oh, okay. Actually I go to full screen because there is animation. Okay, so this one lah. Back again for this slide. Okay, thank you for your mentioning. Okay, so actually this one is what I mentioned before. We call a simple relationship between displacement, velocity, and acceleration. Okay, so for this case, the displacement, green color. Okay, so the velocity and the magenta. So displacement is sine omega t. We differentiate displacement, we got velocity, which is 90 degree out of phase, and accelerations is come out from another integration. Another differentiation, and then is 180 degree out of phase. Okay, so this is the relationship lah. Okay. So this one try to go full screen because there's a lot of video. Is it okay? This slide you can see the
Slide 14. Yes.
Yeah. Is it okay? You can see the slide, the animation, the video.
The video tak boleh sir.
Tak ada. Okay, tak apalah.
No, sir.
I don't know why. Okay, so this one actually just the simple study lah for the vibration, the relationship with the actual lah. So this example for the classical failure lah in vibration issue. So this is due to the vortex shading. Okay, so this is how vortex created by the wind. So when the wind pass to the bridge, it create a vortex, and actually this one can create the harmonics. Okay, so the harmonic, when the harmonic excitation is coincide with the natural frequency, and then it's happen the resonance phenomena lah. It can create the high, very high vibration lah. Actually this one commonly happen in industry. For example, this one is the vertical pump lah, for the oil and gas industry. Actually this one vertical pump is one of the most important parts lah in the processing plant, because every single drop of the crude oil we pass through this pump lah. So it's commonly happen. It's have a problem with the structure issue lah, which is there is a failure in the middle of this pump lah. So this pump there is a motor the middle. Okay, so there is crack here and there lah. So there's a lot of problem. Then after doing the assessment, found that this is the resonant issue lah. So this one actually the actual measurements lah. So the actual measurement, you can put sensor, measure the deflection lah for each point. So you put roving the sensor for each point, and then you can amplify. Actually this is not the by naked eye you cannot see that kind of motion, but using the software you can amplify lah. From that you can see the pattern of motion, which is this one is after measuring is the natural frequency, and found that the motion is coincide with one of its natural frequency, so there is a resonance lah. So this is the way how we analyze the vibration issue, because this one is very high vibrations, is exceed the minimum allowable maximum allowable range. Okay. So this one we call as an operational deflection shape lah. So which is tending to amplify the motion to see how is motion, okay, and relate with the natural frequency. Okay, so from then you can suggest lah the solution for this one. For example, you use a motor as a prime mover. So motor for the application, there is no speed controller lah, so you cannot mean that you cannot control the speed. So mean that to reduce the vibration you have to modify the structure lah. So there is a structure modifications lah. So for this case, the solution is to increase the stiffness in the middle parts so which is at a few whips on this component to add the stiffness and increase its natural frequency in this bending mode. So after that can reduce the vibration. So this one just example for the application of vibration. I'm not sure. Okay, you can see it. This, I go for the full screen. So this one is the soldier causing the bridge. When the step frequency equal to first minimum, and then you can see that the motion. So actually, this kind of technique also been applied to to find the natural frequency for the structure, for the huge structure. Because normally common practice we use the impact hammer to induce the force, but when you deal with a very huge structure, it's not easy to give the sufficient amount of force to excite all the natural frequency. So that's why one of the technique they're using is soldier, because soldier is a very good discipline to create a rhythm based on the frequency. Okay, so play the music for example, and they just put step on the bridge. Okay, depend on the how fast it's depend on the excitation lah. And from that we can measure the response and which frequency can produce the highest vibration response. So that is a resonant frequency lah. So that's the way to do the measurements lah. Okay, and then if the step is equivalent to its natural frequency, then it can create the make it resonance and can cause high vibrations. Okay. And then we go for the another type of motion lah. So previously we just look for the simple harmonics motion. Okay, so simple harmonic motion mostly relates to the single degree of freedom system lah. Okay, but if you go for the measurement in actual condition, it can be periodic and which is and many more type of vibration. So now we go for the periodic motions. Periodic motion actually when there is a same patterns have repetition by the times. So this one we can call as a periodic motion. It's normally happen. So especially when you do the rotating machinery. Okay, so normally for the one complete oscillation you can get this kind of, but this one we call as an amplitude modulation. So amplitude modulations is other commonly happens, or sometimes it can represent the defect itself. But this one is this kind of signal is mostly is the commons for the machinery lah. But sometimes it can use as an indicator to detect the defect lah. For example, the bearing defect, the gear defect lah. And then there is a random motions. So random motion you can classify as a non-deterministic. So which is you cannot represent into mathematical expression lah. Okay, so which is contains broad frequency. So which is this is a lot of combination frequency. Okay, so basically it's unpredictable lah. You cannot predict what happen next if you do the measurements lah. Okay, so this one is an example vehicle on uneven road surface. So because this one is depend on the road surface. Different road surface can produce different vibration level. Okay, vibration with looseness. Okay, so can create this kind of vibration response lah, or the motion. And then chaotic motions. Okay, chaotic motion is combination lah, combination random and periodic. So periodic normally when you deal with the rotating equipments lah, so it have their own motion. Okay, so which is there is one complete oscillation. Okay, they have their own patterns lah. Then when we enter to the next, can repeat the same pattern, something like that lah. If there is a rotating equipments and combined with other type of failure lah, for example the looseness, something like that lah. So can create the chaotic motion. So vibration signal contains all frequency in a given band, but not equal proportional. Okay, so which is have contains lot of frequency, but it's not equivalent for each frequency components. Sometimes there's a certain frequency a high frequency, other frequency is a low frequency, because normally for the periodic have the dominance frequency, and then for the randoms is a frequency is broadly spread lah, which is for the random it's almost same lah, but when you combine with the periodic, then can have a dominance and plus the broad range of frequency lah. Then there is a transient. Okay, so transient when you hit something and then you can have this kind of impulse impulsive. You give the impact force. Okay, some kind of impact force normally it's come from the impact force. And actually for the to determine natural frequency for the system, normally we use the impact force so we give the impact and then let the structure oscillate. Okay, so because the structure have their own natural frequency, when you give the disturbance or you give the impact, and it will vibrate at their own natural frequency. So from that we can determine what is the natural frequency of the structure. So that's commonly used the way we measure the natural frequency of the structure. Okay, so we give the impact force, or otherwise you can use the random force actually. So that is other two method lah. So this one mostly come from the free vibration. So you just give the impact and then you release, and it's keep vibrating lah. And the way it's vibrate is depend on its natural frequency. Okay, then there is also beats beats phenomena. So beats is happen when two harmonics motion with the frequencies close to one another added lah. So which is can resulting the motion called as a beats Okay, so beats basically when you go for the industry, it's commonly happen when you deal with the for example, you have a two motor. Okay, so two motor you put side by side. Okay, and the frequency of rotation should be same lah. But for the certain cases, there is a bit difference of in terms of frequency between two. It's not equivalent. It's should be identical actually, but due to the certain issue, for example, the friction, something like that, it can create the lag of the motion so which is can create the two different frequency. When two different frequencies run together, you add it and then it can create the beats phenomena. Okay, so the beats phenomena, which is it can amplify the signals or the response for example, when you have two kind of harmonics, okay, for example, this one is a 10 hertz 10 hertz. This one 10.5 hertz, and then after then it can be similar like this Okay, so you can create the beats phenomena. The closer the difference, for example 10.1, it can create the beats period is it will be greater beats period lah. So actually this one is it can create the high vibration because it can amplify twice of its amplitude okay. So if there is a x plus x, it can be 2x the total of vibration amplitude can be very high. Okay, but from that it also can create the the misinterpretation so in the vibration measurements, I have experience measuring vibration in chemical processing plant and then face this beats issue and then the frequency is very close, which is the beat period is taken around 3 minutes to complete one of the beats period. Okay, actually in the vibration measurement, if you want to measure the vibration intensity, the common practice only measure a few seconds only, okay, 2 4 seconds around that, and then uh state the reading lah. Okay, so the problem is you can misinterpret the data. Okay, so because when you do measurement at this period, okay, so you can declare this is a low vibrations because you measuring at this, you take a sample at this point, so which is can give the wrong interpretation lah, but actually it can reach up to this level. Okay, so even if you do the measurement at this level, uh it still cannot represent the whole ni lah, the whole issue lah. Okay, because this is high vibration but it's not constantly happen so because after that it reduce and we increase again, so that's the problems so we can create uh it can amplify twice of its vibrations level. Okay, so for this solution you have to do the rectifications so rectifications, and because this one you cannot control the speed, so you have to isolate the motor lah, so to ensure that the vibration from one of the motor didn't transmit it to another motor lah, so which is from that you have to isolate the motor. By isolating, then you can the vibration from another motor is not transmitted to another lah. Okay, so that commonly solution lah in industry. Okay, so that's the kind of motion response. So now we go for the degree of freedoms. Okay, so degree of freedoms. We can define as the minimum number of independent coordinates. So which is the possible motion for the system. Okay, so for example, I have this mouse, and if there is a spring, and this mouse only restricted to move in the vertical directions, so it can just move up and down. Okay, so we can declare as a single degree of freedoms. Okay, so single degree of freedom. But if at the same time this mouse also can move in the another plane lah. Okay, so in the horizontal plane. Okay, so this one we can consider as a 2 degree of freedom because have two independent coordinate, which is motion for the vertical and motion to the horizontal. Okay, and if at the same time it can also rotate like this, can declare as a 3 degree of freedom because there is another independence coordinate lah, which is can move in it can rotate like this or it can twist like this, and we can add another degree of freedoms. Okay, so that's what we call as a degree of freedoms. So it's depend on the independent coordinate vibration system, which is can be divided by the following lah. In this subject, we divided by we clustered by 3 type of degree of freedom lah. So which is single degree of freedom, so which is only we stated simple system lah, just a single degree of freedoms, and then multi degree of freedom continuous system. So continuous system we not cover lah actually, but it's commonly used in solution lah, and normally we use the software like finite elements lah to represent the continuous system lah. Okay, so normally we use single degree of freedom, multi degree of freedom lah. Okay, so multi degree of freedom meaning that more than one lah, for this case is and cover up to only 3 degree of freedom. Okay, so this is a sample for the single degree of freedom. Okay, so spring mass system. Okay, and then this mass have a tendency to move in the vertical directions. Okay, so this one is a single degree of freedom if only can move in the vertical direction lah. This one for the translation motion, and can be also rotational motion or torsional motion lah. So this one disc and shaft. Okay, so the disc can rotates. Okay, so the deflection here is measured in the units of radians lah. For the translation, we measure in the unit of displacement lah. Displacement mostly used in SI unit meters, and for the torsional motion, we measure by unit of angle. Okay, so unit of radian lah for this case to measure the deflection. And this one is 2 degree of freedoms. Okay, so 2 degree of freedom example for the translation motions. Okay, rotational motion for the torsional system lah. And this one also 2 degree of freedom. Okay, so this one is we call as a coupling lah. So coupling coupled system. So which is have a combination of the translation and rotational motion lah. So for this case, if you give the disturbance to the system, this slender rod will rotate, and this mass will move in up and down direction. So this one is a translation motion, and this rod will move in the rotational motion. So these three type of possible motion for the 2 degree of freedom system. Okay, so this is a 3 degree of freedoms. Okay, so same goes with 2 degree lah. So just add another torsional and also another mass lah. And this one pendulum system also can be defined as a degree of freedom lah. So 3 degree of freedom because it have a 3 mass. Okay, so you can produce 3 different angle displacement: theta 1, theta 2, and theta 3. Okay, so same goes here for the which is theta 1, which is referred to the motion of the first disc, and theta 2 represent the motion for the second disc, theta 3 for the third disc. Same goes for the translation. We use x1 which is deflection, displacement for the mass 1, deflection for mass 2, and deflection for mass 3. And actually you can have a combination like couple system for the 2 degree of freedom lah, but I can list all of them. And then the continuous system, so it defines infinite number degree of freedom lah, normally used for the FEA simulation lah. So which is we can it's depend on the nodes lah. So you can define the nodes. Okay, so each node have their own motion lah. So for example, this one is a beam, so beam have their own deflection lah. Okay, so you measure deflection at point 1, point 2, point 3. So this can give you the motion for each node. So this one actually very important because you can relate the motions with its natural frequency lah, because every natural frequency have their own mode shape. Okay, so it can be, for example, this kind of beam. So it can bending like this, the first bending mode. Okay, or you can bending like this. So you can have a bending like this, second bending mode, third bending mode, and so on lah. So every mode have their own natural frequency. So for example, if you excite, if this beam have the second natural frequency, this one is second mode shape. So second natural frequency, for example, is 10 Hz. Okay, and then you put a motor on this beam. Okay, and then you set the motor speed, which is you try to excite 10 Hz. Okay, when you excite the 10 Hz, and there is a resonance phenomena because you excite, then the excitation from the motor is coincide with the natural frequency of 10 Hz lah. So what happens to the this beam? It will have a deflection in the pattern of this mode. Okay, so which is it will deflect like this. So this kind of bending. Okay, so it bend like this. If you excite the first natural frequency, for example, the first bending mode, and then it will bend like this. So that's the relationship with the natural frequency and its mode shape lah. So that's why it's very important to know the pattern of motion lah. So we call as a mode shape. Same goes for the, if you still can refresh the Tacoma bridge, you can see that the bridge have something like this. It's twisting, right? A twisting. So it's due to it have the twisting mode at the certain frequency lah, which is the resonant frequency induced by the vortex shedding from wind. So which is the frequency of vortex shedding is equivalent to the twisting mode. That's why you can see that the bridge in the is twisted lah. So you can see that the motion. So that's the relationship. So this is the way how we represent the motion. So the dynamic study. Actually, this is not part of syllabus in this subject, but for your knowledge, it's good for you lah. Okay. So for this subject, we only cover up to 3 degree of freedom system lah. Okay, so now we know that the means the degree of freedom. So now we go to the modeling the dynamic system. Okay, so this one is very important because when we see the dynamic system, the most important thing we have to model it. Okay, so to find what is the mass elements, the spring elements, and the damping elements lah. Because from that you can estimate the system and do the modification and another rectification lah to increase the system. Okay, it's depend on the requirements lah. If you want to go in very detail, then you can create a very detailed model. But if you are interested about the just a few kind of motion, and then you can simplify the model. Okay, for example, this part is the car. Okay, so we can represent as a simple single degree of freedom system. So which is, if we are only interested about to study the motion of car only in the vertical direction lah. Okay, so we can model like this. So which is, for this case, we take the equivalent mass as the total mass and then the stiffness, total stiffness applied from the car, which is come from the suspension. Okay, the tire itself, and then we can model. Okay, so from that we can estimate what is a natural frequency, for example. Okay. But normally car will not model a single degree of freedom lah. But normally if you deal with the machine equipment, for example, and this is commonly we can define as a single degree of freedom system lah. For example, the lathe machine, okay, and the CNC machine. So because you can model as a single degree of freedom lah, because you have a support and you have a motion. So you can estimate the natural frequency, and we have to try to avoid that kind of frequency to avoid the high vibration. Okay, so this one is for the single degree of freedom. Then you can model as a multi degree of freedoms. So which is you can consider that the motion of the front part and rear parts. Okay. So this one is split by two lah, front suspension and the rear suspension. Okay, so S1, S2, which is represent the motion for the front and the back. Okay. Oh, and then can go for the many degree of freedoms. This one you can split by tire and by the car body. Okay, so this one is actually the I think the minimum lah, minimum model for the car. So from this one, you can study the motion for the tire, okay, and then the motion for the car body, okay, because if you uh, sometimes the car, especially you look at for the luxury car, okay, so you can see that the car still the body of the car doesn't vibrate even the tire have high displacement lah. So that's due to the study of this part lah. So which is the way um, you design the suspension system to ensure that even the tire have high deflection, okay, the amount of the transmitted uh, force from the tire is a minimum lah. So which is can give comfort for the driver or the passenger of the car. So which is you have to know that what is the sufficient normally it's control to the damping lah. So you have to put the sufficient amount of damping lah to ensure that there's very minimum force is transmitted to the car body, okay. And to go in details, we can study about the seat lah for here. Mostly we study for the about comfort lah, the comfort. So we just measure about the vibration received by the driver to ensure that is it comfort or not lah. So this commonly happen in we call as human body vibration lah. So human body vibrations to study the dose of vibration received by the passenger lah, or the driver. This one you can split by model lah. So which is the seat. And you can go for the pitching mode lah. So which is is have a pitching mode. Actually, this one is very important, especially if you want to study about the mass distribution lah. Okay, so that's why in designing of a car, it's not just about the total mass, but the way you distribute the mass, the center of gravity. Okay, so this one actually can can reduce the impact lah during driving. So there is a parameter called center of percussion. Okay, center of percussion, which is if you can put your center of gravity at the right point, and then actually when you hit the bump, it's automatically those design can absorb the effect of bumping. Okay, same goes when you design the baseball bat, for example. Okay, so baseball bat, the good design, when you hit the ball, the reaction force received by your hand is less lah. So that's the same concept lah. So that's we call as a center of percussion. So this one for more detail lah, you can study about another degree of freedom to model, which is to measure the angle, so the rotational motion. Okay, so this is how the model of vibration lah. So it's depend on you lah. If you deal with a certain system, what is system of interest, what is vibration, the most important components lah. You want to protect, you want to know the in detail, then you can model. And once you model, you have to identify what is the equivalent mass, the equivalent stiffness, then the equivalent of damper lah, the damping. I think that's all for the today lecture. So I think the second chapter we go for the next week. Okay. So for today, we have looking for the type of motion. So which is the harmonics motion. How you see the harmonics motion, and then the how to represent into mathematical model. Okay, and then we go for the degree of freedoms. Okay, so degree of freedom, how we define the degree of freedoms and how we model model something like this. So sometimes if you go a very complex system, actually you can just simplify lah, simplify. You can represent as a single degree of freedom, for example, to solve the vibration lah, the vibration issue. Doesn't mean that you go for the more detail you can get the best result lah. Sometimes less is simple. For example, I have do the rectification on the vertical fan, for the industrial vertical fan to cooling the lip oil for the general bearing, no? Okay. And then the design is something like this. Okay, so have a motor as the prime mover. So this is a motor. And then this is pulley connected to the shaft lah. Okay, shaft. And then this is fan. And this also have a resonant issue. Okay, so the motor is fits to the structure like this. Okay, so so this is a motor. This is a fan. Okay, and then it have a high vibration in this direction. So which is dominated by horizontal motion. Okay. And then have a vibration issue, which is there is a crack here, crack on this motor support. So this is a crack issue. So this is due to the high vibration. Okay, so to rectify, actually you can just model all of this model as one mesh. And spring system lah, like this. Looks complex, but it's still useful lah. Okay. So this one fits to the another structure lah. So the stiffness is depend on the stiffness of this structure lah. Okay, so this part and this part lah. So you can increase lah. So which is you can add a stiffness. Okay, you can add the stiffen the structure. Add something like this, and then you can get a new K equivalence. So if the K equivalence, then you can estimate the new natural frequency. Okay, so the new natural frequency, and then if the new natural frequency is more than the current natural, because this one is resonant. I believe it's around 7 hertz. And then we want to make it natural frequency is away from 7 hertz lah. So after rectification doing, and we found that it can goes to up to 12, and then 12 is enough lah to because after change natural frequency, then when you run the system, you have a less vibration because the resonant frequency is away from operating frequency. So that's the way we can model the system lah. Okay, so even you deal with a complex system, actually you can still simplify the system, okay, and then can propose the good solution lah to solve the high vibration issue. So from this, that's why it's very important to know that the modeling of the system lah. But for the car, of course, you need a very detail lah. So because to do the simulation lah, so you can do the simulation, a lot of metrics here, and then you can change the value for C, K, and then you apply the force here, and then you can see what happened to the motion for this car body is sufficient or not. So that's the way vibration study lah in the designing stage lah. Okay, so any question? I think that's all for content for the today lecture. Okay, so we already finished for the first chapter lah. Okay, so next chapter we go detail on about the elements lah, elements of vibration, and then we start with the calculation on the weight tree lah. Weight tree we go for the single degree of freedom system. Okay. So your midterm only cover for the single degree of freedom lah. Single degree of freedom actually you cover for the first free vibrations, and then for the undamped system lah, undamped, and the force vibration for the undamped, and then cover up to free vibration for the damped system lah. So we actually there is another force vibration for the damped system lah, but that one we cover on the final exam.
Sir, dekat mana boleh dapatkan slide tu?
Slide nanti saya letak dalam Google Drive. Sebab saya nak complete dulu, and then save, then bisa masuklah satu slide untuk after finish lecture.
Okay, baik, terima kasih.